Hey everyone, welcome back to our APIGURU channel. For those of you who are new here, I'm Damien Thorn here. On this channel we share everything you need to know about APIs. Today we will review the risk of the top 10 API security threats and how to mitigate them. Let's get started. OWASP is a community focused on helping organizations create and maintain trusted applications and APIs. Through its API security project, OWASP identifies critical security risks and offers mitigation recommendations. Let's get started with the broken object level authorization risk. Attackers can exploit broken object level authorization by substituting the resource ID in an API call with another user's resource ID. The absence of proper authorization checks allows these attackers to access unauthorized resources. This vulnerability is referred to as insecure direct object reference. Broken object level authorization, short BOLA, is one of the most common security threats, representing nearly 40% of all documented API attacks. Since 2019, BOLA vulnerabilities have consistently ranked at the top of the OWASP list, continuing to hold this position in the latest OWASP API Top 10. Let's assume an API is designed to provide financial information for shops. A legitimate user can use their shop identifier to access data related to their shop. However, an attacker could manipulate the shop identifier and access financial information from all shops, provided the API does not have adequate permission checks. This issue is worsened when resource identifiers are easily guessable or sequential, allowing attackers to systematically attempt various identifiers and retrieve confidential information from other users without any safeguards. Organizations should implement robust authorization checks utilizing user policies and hierarchies to mitigate this risk. Avoid relying on IDs sent from clients. Instead, use IDs stored securely in the session object. Verifying authorization for each client request to access the database is crucial. Employing random IDs such as UUIDs can further reduce predictability. A comprehensive testing framework must also be established to identify this vulnerability. Next is the broken authentication risk. Ineffective API authentication can enable attackers to impersonate users or access resources without authentication. Vulnerabilities may arise from unprotected APIs considered internal, weak authentication mechanisms that deviate from industry best practices, and API keys that aren't regularly rotated. Other issues include weak passwords that are either plain text, poorly hashed, or shared, and authentication methods vulnerable to brute force attacks or credential stuffing, including credentials and keys in URLs, failing to validate access tokens including JWTs, and using unsigned or weakly signed non-expiring JWTs further exacerbate the risks. To mitigate these risks, ensure that all potential authentication methods for APIs are thoroughly examined. APIs involved in password resets and one-time links should be protected with the same rigor as other authentication points. Implement standard practices for authentication, token generation, password storage, and multi-factor authentication. Utilize short-lived access tokens, authenticate applications to identify the source, and enforce stricter rate limiting for authentication attempts. Additionally, lockout policies should be implemented and weak password checks should be conducted to enhance security. Now let's talk about the broken object property level authorization risk. API endpoints can be susceptible to attacks due to excessive data exposure or mass assignment vulnerabilities. Excessive information exposure occurs when APIs return more data than necessary for their intended business purposes, while mass assignment happens when APIs inadvertently accept and process data beyond their scope. Consider an example where an API returns complete data objects stored in the backend database. The client application is designed to filter these responses to display only the necessary information to users. However, if attackers directly call the API, they can retrieve sensitive data that the UI would typically filter out. To prevent these vulnerabilities, never rely on the client to filter data. Review all API responses to ensure they only provide what consumers need. Carefully define schemas for all API responses, including error responses. Identify sensitive data or personally identifiable information and establish a robust data governance process to justify its use. For incoming requests, avoid automatically binding incoming data to internal objects. Explicitly define expected parameters and payloads. Use the read-only property in object schemas for fields that can be retrieved through APIs but should never be modified. Define schemas, types, and patterns at design time and enforce them at runtime to maintain security. Moving on to the unrestricted resource consumption risk. APIs that lack protection against excessive call volumes or large payload sizes are vulnerable to denial of service attacks, as well as authentication exploits such as brute force attacks. In a brute force attack, an attacker systematically attempts numerous combinations of usernames and passwords until they find the correct one. DOS attacks can render services unavailable, resulting in downtime and significant financial losses. Attackers can overload the API by sending more requests than it can handle, overwhelming its processing capacity. They might exceed the API's rate limit, causing significant delays or failures. Additionally, attackers can submit requests with huge payloads or complex queries, leading to bottlenecks that result in dropped requests. To mitigate these risks, implement rate-limiting policies across all endpoints, particularly authentication endpoints, which are prime targets for attackers. Customize rate limits based on the specific needs of different API methods, clients, or addresses. Since IPs can be easily forged, consider applying rate limits based on unique identifiers such as fingerprints or tokens. Additionally, to prevent excessive server load, set limits on payload sizes and the complexity of queries, primarily in GraphQL, must be imposed. Define CPU and memory limits for containerized and compute resources and restrict pagination sizes and total page counts to control data retrieval. Finally, leverage DDoS protection services provided by your cloud provider to enhance overall security. Next is the broken function level authorization risk. The API depends on clients to correctly use user-level or admin-level APIs, which can create vulnerabilities. Attackers can discover hidden admin API methods and invoke them directly. Consider an example where certain administrative functions are exposed as APIs allowing sensitive operations, such as a resource deletion, to be accessible externally. If non-privileged users learn these API endpoints, they can execute unauthorized actions simply by knowing the URL or altering request parameters. Do not rely on the client to enforce administrative access to mitigate this risk. Instead, implement a default deny policy for all access. Ensure that operations are only permitted for users of the appropriate roles or groups. Additionally, design and rigorously test your authorization mechanisms to ensure they effectively restrict access to sensitive functionalities. Let's move on to the unrestricted access to sensitive business flows risk. A set of APIs can expose critical business processes, making them targets for attackers who may exploit them using automated methods to achieve malicious goals, such as data exfiltration or market manipulation. An attacker might discover an API that facilitates online purchases and automates bulk purchases of a newly released product, later reselling it for profit. Similarly, an attacker could scrape price data from a real estate website over time to predict market trends. Automation enables attackers to execute actions more swiftly than human users, granting them unfair advantages on auction platforms and similar sites. To mitigate these risks, first identify business flows that are vulnerable to abuse and implement additional layers of protection. Ensure that authentication is enforced using robust auth flows, such as the authorization code flow. Protect APIs with stringent rate limiting to control access. Monitor API usage closely, restricting access from suspicious devices or high-risk IP addresses. Additionally, non-human usage patterns, such as transactions occurring at impossible speeds, should be identified, and capture or other human verification methods should be implemented to secure the APIs further. Next is the server-side request forgery risk. Server-side request forgery vulnerabilities arise when an API fetches a remote resource without validating user-supplied URLs. This can allow attackers to manipulate the application into sending crafted requests to unintended destinations, even those protected by firewalls or VPNs. If an API accepts a URL parameter for redirection, an attacker could exploit this to redirect responses to a malicious site that steals sensitive API data. An attacker could force the API to load resources from a server they control, facilitating critical injection attacks in JWTs. If an API inadvertently allows access to the local host, an attacker might craft requests that access local resources. To mitigate SSRF risks, define and enforce strict schemas, types, and patterns for incoming requests at both design and runtime. Prevent the API server from following HTTP redirections and implement an allow list for permitted redirects or accesses. Restrict the allowed URL schemes and ports, ensuring that only safe options are permitted. Finally, use a secure library for resource loading that disallows access to the local host and relies on sanitized URLs processed by a trusted URL parser. Let's talk about the security misconfiguration risk. Poor API server configuration creates vulnerabilities that attackers can exploit. For example, unpatched systems and unprotected files expose vulnerabilities, while unhardened container images may include outdated services. Missing or misconfigured TLS can allow plain text data transmission, and exposed storage or management panels risk unauthorized access. Additionally, inadequate course policies and security headers heighten susceptibility to XSS attacks. Detailed error messages can leak sensitive information, and unnecessary features like FTP broaden the attack surface. To mitigate these risks, automate the hardening and patching processes across the entire API stack, including code, libraries, and containers. To avoid misconfigurations, implement automated tests to check API endpoints, such as TLS versions and cipher settings. Turn off any unnecessary features and restrict administrative access. Additionally, clearly define and enforce output formats, ensuring error messages do not reveal sensitive information. Next is the improper inventory management risk. Attackers often target non-production versions of APIs such as staging, testing, or beta environments, which may have weaker security protections than the production API. Let's give me an example. DevOps practices and cloud technologies simplify the management of multiple deployments, such as development, testing, and staging. However, backward compatibility often requires keeping all the APIs active, even if they aren't properly maintained. These outdated endpoints may still access production data, posing a security risk. Attackers might authenticate with a non-production endpoint and then switch to an inadequately managed legacy API, gaining access to sensitive production data. To mitigate this risk, maintain an up-to-date inventory of all API hosts and limit public access to non-production environments. Restrict access to production data, ensuring clear segregation between production and non-production resources. Implement additional security measures such as API firewalls. Properly retire old API versions or backport necessary security fixes to them. Additionally, enforce strict authentication protocols and use redirects and cross-origin resource sharing wisely. Lastly, we have the unsafe consumption of APIs risk. Modern API-based systems are often highly interconnected, relying on upstream APIs that may themselves have vulnerabilities, potentially compromising their consumers. For example, an upstream API might inadvertently store sensitive data provided by a consumer, violating data governance regulations. Additionally, if an upstream API provider is compromised, it could pass malicious data to its consumers due to inadequate internal controls, such as in the case of a SQL injection attack. Treat upstream API data as untrusted, filtering and sanitizing all input to protect against injection attacks. Ensure upstream API providers specify their API contracts and implement the runtime mechanisms to enforce these contracts. View upstream providers as part of your supply chain, verifying their internal development processes. Always use secure communication channels to protect data in transit. Understanding and addressing these top 10 API security threats is crucial for protecting your applications and data. By implementing the recommended mitigation strategies, you can significantly reduce the risk of vulnerabilities and enhance the security of your APIs. Remember, security is an ongoing process, and staying informed is vital. Thanks for watching. If you enjoyed this video and want to see more, hit the subscribe button and turn on notifications so you don't miss any updates. Please give this video a thumbs up if you found it helpful, and let me know in the comments what you think or if you have any questions. Look out for our next video, in which we will explore the benefits of having an API platform.